This is Chapter 8, Section 8, our last section in this nice long chapter. And we talked about compound interest, where it has a formula A equals P times 1 plus R over n to the nt, where A, P, N, and T all stand for things. I guess I didn't say in here. Forgot to mention that R is your interest rate. Always write that as a decimal. People tend to forget that. Well, that's if interest is compounded in some sort of a frequency, like once a month, once a year, 4 times a year, something like that. If there's some frequency, some intermittent compounding frequency, you'll use this formula over here. But if interest is being compounded continuously, meaning each and every single passing moment, at every instant, continuously you're compounding interest, then you use this formula here. P still means the same thing, and R and T all mean the same thing. But instead of having an end, since the number of times we compound in a year is technically infinite, this is where that E comes in. Because remember how we talked about in our last video that 1 plus 1 over infinity to the infinity, this is actually the number E. It comes out to that limit of E, 2.718. So we use this formula to calculate continuously compounded interest. So over here, if you invest $16,000, earning 6.25% of continuous interest, well, then I'm going to use this formula here. Our final amount is our starting amount times E to the RT. It's often called PERT. How much money do you have after 10 years? Well, then our amount is going to be, our starting principal P is 16,000. Then we're going to do E to the 0.0625 times 10. The common mistake here is not putting parentheses in your calculator in the right spots. I'm going to do 16,000, I'm going to be in my way equals menu though, 16,000, and then times E to the, so second ln, E to the 0.0625 times 10 in parentheses. The nice thing about doing second ln is when you do E2, that pulls up this parenthesis here, and that's really nice. I calculate that there's $29,891.93. So after 10 years, your money gains $13,000 at 16% interest. Just for the record, had it's been compounded not continuously, but let's just say even monthly. Had it's been compounded monthly, this would be 1 plus 0.0625 divided by 12. I'm just doing the compound interest formula here. To the 12 times 10. It would have been $29,843. So it makes a difference of $48, which is not a lot of money. It turns out the more often you compound, it doesn't have a huge difference in the amount of money you make, but it can make some difference, especially if you're doing it for a very long period of time. Okay, how long till your money doubles? Well, assuming we're still starting with our 16,000. If we're starting with 16,000, we're doing times E to the 0.0625. Well, now we don't know how much time we're talking about, so we put our variable T here, and we know that we want to end with 32,000. Now I solve this equation with T as a variable. Well, my T up here is a power, so I have to solve using some logarithms. I'll start first by dividing everything by 16,000. I can't take a log of anything until the thing with the power is being all the way isolated. So I divide both sides by 16,000, I get 2 equals E to the 0.0625 T. And you'll notice that basically the amount of money I started with didn't matter. Since it doubled, I just end up with a 2 over here. We'll talk about that more in a second. We want to take a natural log of both sides to undo that E. The inverse of E is ln basically. And I end up with the natural log of 2 equals 0.0625t. So I'll do the natural log of 2 divided by 0.0625. Let's see what that is. $11 years, 11.1 years. Which makes sense, because at 10 years up here, at 10 years, we'd almost doubled. We're only 3,000 away from doubling, so it's going to take more than 10 years, but not much more than 10 years. Now that was starting with 16,000. At that time we started with 16,000. But suppose we take that amount and we change it to 30,000. Well, then how long does it take to double? What's really cool about exponential functions is when we're talking about doubling, you're really talking about multiplying by 2. So we're going to want to end with 60,000 and start with 30,000. Didn't really need that fancy there, but there it is. Well, still when I do the division, these cancel and I get 2 again. I'm going to have the exact same answer I had before. It doesn't matter how much money you start with. If you're wanting to like double or triple or increase by some sort of multiplier, the starting amount of money or anything doesn't matter. It'll be the same amount of time no matter what. So that's a good property to understand. If you're not dealing with money, these formulas are going to be the exact same, but there's lots of things in nature that do continuous growth or continuous decay. So we have the function f of t equals ae to the kt for growth, and f of t equals ae to the negative kt for decay, and that negative is what makes things go down instead of up. And you'll notice how similar this is to PERT. I mean, A stands for starting amount, and P stands for starting amount. K is called your rate of continuous growth or rate of continuous decay. That's what we called R before. R was an interest rate. T is still time. Everything's the same. We're just using slightly different letters. This is done with carbon dating of objects all the time. So carbon-14, this is called carbon-14, is a type of radioactive material that has a half-life of 5,730 years. What that means is if you started with, say, 100 grams of carbon-14 that was decaying, after 5,730 years, you have 500. I started 100, so I'd have 50. Another 5,730 years, you have 25. And another 5,730 years, you have 12 and a half. And then 6 1/4. And then 3 1/8. And then whatever's after that. And it's always going to decay by half. But as it's decaying, there's always going to be something left. It's going to have an asymptote getting closer and closer to 0. That's what exponential decay was. So we can use this idea of half-lives, how long it takes something to get cut in half, to calculate how much stuff there was a long time ago. So the half-life of carbon-14 is 5730 years. So that means that if we start with, let's just say, A, that's our amount of carbon-14. If we start with that much, we'll call it A for amount. Well, I know that after 5,730 years, I will have half of it. I know that after 5,730 years, I'll have half of what I started with. And right now, I'm going to solve for this k right here. And this seems kind of weird, because right now it feels like there's 3 variables in this equation. But there's really only 2 variables right now, because e is a number. This is not a variable. This is a number. And you're going to find that these a's are going to cancel. So the first thing I'll do is divide both sides by a, and that gives me 1/2 equals e to the negative 5,730k. You actually don't have to start with these a's like I do. I'm just showing that because that's really what's happening. But you can just start with these half-life problems with that right there. Now this, I'm going to solve for k. So I'll take a natural log of both sides. I'm going to write this a little bit smaller. I'll go with blue again, I think. I'll do the natural log of 1/2 equals the natural log of e to the negative 5,730k, which means that the natural log of 1/2, well, the L and the e kind of cancel each other, and this negative 5730 can come out in front, so it equals negative 5,730k. The natural log of 1/2 is going to be a very small number, and a negative number. Sorry, I did +0 because I put the plus on accident. The natural log of 0.5 is negative 0.69. Divide that by negative 5,730, and you get a very small number. 1.21 times 10 to the negative 4, scientific notation, times 10 to the negative 4. So I'm going to say that k equals, if I move the decimal 3, 4 to the left, there's 3 zeros, 0.000120121, I'll say. I'm going to round a little bit. I did all that work to find that k value. Once I have the k value, I can write the equation. It's f of t equals ae to the negative 0.000121 t. And now with this equation, if I knew either how much amount I started with, I'd know how much time I could find. Or if I knew the time, I could go back and find how much I started with or ended with. So that's your equation. That's how you find your equation to work with half-life functions. So I'll do another longer example. There are 48 milligrams of carbon-14 in the bones of a house cat. That's a number that I made up. A fossil of comparable size has 1.2 milligrams of carbon-14. How old is the fossil? Let me pause here for 1 second. So the idea here is if there's, this cat has 48 milligrams right now. So it's starting at 48 milligrams. But then it's decaying. We're using the formula that we had from our last problem. If I take this formula here, negative 0.000121, since we're still doing carbon-14, I'm going to use the same formula, 3 zeros, 1, 2, 1. So I have y equals ae to the negative 0.000121 t. Well, my starting amount is now 48. This is how much I'm starting with. My ending amount was 1.2. It went way, way down. And so I can solve an equation for t. One there at the end. So first I'll divide both sides by 48. Look here. And I get that 1.2 over 48 is going to be 0.4, I think. Let's just make sure. Shoot, I broke everything. Good, didn't take too long. 0.25, 0.025, yeah, that makes sense. 0.025 equals e to the negative 0.000121 t. I'll take a natural log of both sides. The natural log of e is just 1. So I solve for t. Actually, I want u. So I'll do the natural log of my previous answer divided by negative 0.000121. And it's 30,486 years. This is essentially how carbon dating works. You take an object that you find from a living thing that was dead, and once it dies, it starts decaying. And as the decay passes over time, we can compare the size of this fossil to the size of something living today, and see how much carbon-14 there should be, and then do some carbon dating to figure out how old the creature was, or whatever it is that we're trying to measure. Do a different example now. A fossil has 5% of the potassium-239 that it would originally have. If the constant of decay, this is right here is our k value. This is that k value, this is given to us. If the constant of decay is 2.888 times 10 to the negative 5, how old is the fossil? Well, basically I know that if my starting amount was a, I'm going to end with 0.05 of a, because that's 5%. If we've lost 95%, we're keeping 5%. We have 5% of the stuff remaining. So I can really just set up the equation 0.05 and not worry about the a values. You know, I'm always using this formula here, but this y is going to become 0.05a, and this would just be a. And when I divide by a to start, the a's cancel. So let's just jump straight to here. my k value is now 0.00002888 to the t. The question is how old is the fossil, so I solve for t. I get that the natural log of 0.05 is equal to negative 0.00002888t. I just skipped taking the ln of both sides. So I divide both sides by this number, and I get the natural log of 0.05 divided by this enormous number that I'm getting sick of writing. Do that math. $104,018. Number here. So t is about equal to 104,000 years. Carbon dating, or in this case potassium dating, but radioactive decay, radioactive dating is pretty crazy. This can also work for populations. I'm still just going to use y equals a e to the positive kt, because this time we're growing. In 2007, Georgia had a 9.36 million population. In 2000, it was 8.18 million. So in 7 years, it went up over a million, 1.2 million just about. So I'm going to write the equation that models Georgia's growth over time. Well, my starting amount A is 8.18. So I have 8.18 times E. I'm going to try and calculate K. K is what I'm trying to find. I know that T is 7 because 7 years passed. My ending amount is 9.36. I'm not going to bother writing out all the millions because they're just going to cancel anyways when I do all this division. So I can just leave it like this. I'll take them smaller now. So I divide both sides by 8.18. And I get whatever that is. Really? Come on, Grant. Better than that. 1.144. We want to put down a lot of decimals for these numbers because they matter. In fact, I'm going to go here, I think. I'll just call it 7k now, e to the 7k. Take a natural log of both sides. The nice thing is, even though I'm not writing out this whole number here, it's still stored in my calculator. So if I don't use my calculator until this last step, when I do ln of 1.1443 divided by 7, I can just do the natural log of the previous answer and divide that by 7. And I get 0.01925. Now my equation for growth is y equals ae to the 0.01925t. I get to the next question now. How long until Georgia has 10 million people? Well, if in 2007 it had 9.36, that's my starting amount. This will be a t now. I'm trying to find time. So I'm going to put a t here. And I know that I'm ending at 10. Well, how long until it has 10 million people? I just solved this equation with the starting amount and ending amount, and then my constant of growth that I found in the first problem. So with almost all of these problems, the first issue is to find the k value. Once you found the k value, you kind of rebuild your equation and go from there. I'm going to do 10 divided by 9.36. I get that. I'm going to do the natural log of that, and I have the ln, natural log of 1.06837. Go 038, I'm going to round, is equal to e, well, the natural log of that side also. The natural log of e to the 0.01925t. So we really just have natural log of 1.06838 divided by 0.01925 is going to give us our time t. So the natural log of this number and divide it by 0.01925. It's going to take 3.4 years. So not too long for this 10 million. In fact, we could look up the population of the state these days and see if it kept to that growth, but I'm not going to bother with that for now. So there's that. Do we have any more? Nope, that takes care of it. These examples are ones that you should probably look at over and over and over. I know this is a long video, but I think you're going to want these examples a lot.